Hi guys, welcome to this lecture. This is about, once again, the same topic that we've been dealing with, law of heat exchange, except that this is a slightly harder problem in the sense that it involves a little more understanding of the events, and so I thought I'd put that out as an example and see if you guys can understand. I have put some information up here to begin with, just so it takes less time to complete it. I'm going to try and finish it in a single lecture. Okay, first of all, starting with a question, it says a beaker contains 250 grams of water at 25 degrees Celsius. An ice cube at negative 4.4 degrees Celsius is added to the water. After the ice has completely melted, pay attention to that. The temperature of the system is found to be 23 degrees Celsius. Assuming that water-ice system is insulated, determine the mass of ice added. Okay, so first of all, it's not asking you for the final temperature this time. It's already giving you that. It wants to know how much ice will be added. So important things to note, first of all, like I said, it talks about ice being completely melted. And the second thing is that we're talking about the water-ice system is insulated, which means that we're assuming that no energy is lost to the beaker, to the air above it, or anywhere else. All the energy is contained within the ice and the water. Okay. And it has given you some constants here, the specific heat capacities of water, that of ice, and it's also given you the specific latent heat of ice. Now why? We'll just see that. Okay, so here is what I have. The way I've set it up. Ice is at negative 4.4 degrees Celsius. Water is at 25 degrees Celsius. Which is hotter? Which is colder? Well, of course, the ice is only at negative 4.4, which is very cold. Water is at 25 degrees Celsius, so even though it's not hot, it's still warmer than the ice, and therefore the direction of flow of energy will be from the water into the ice. Okay, so that's the first thing we need to determine. Which way will the energy transfer? So, now, talking about the law of heat exchange, water will lose energy, and whatever it loses will be gained by the ice. Okay, so let's put some numbers down here just so we know what we're looking at. The water has a mass of 0.25 kilograms. It says 250 grams, which is the same thing as 0.25 kilograms, so I've already converted. Initial temperature of water is 25 degrees Celsius. Final temperature of water is 23 degrees Celsius. And the specific heat capacity of water is that much. Okay, and notice that we have Kelvin here and we have Celsius here. However, like I pointed out before, since it's a change in temperature, it's delta T we are talking about, so there shouldn't be any difference whether it's Celsius or Kelvin, because the change in temperature on either of those scales is exactly the same. It's the starting point that's different, but not the change in temperature. Okay, so ice is the other item we have. The mass we do not know, that's what we're looking for. Initial temperature of ice is given as negative 4.4 degrees Celsius. Final temperature is 23. Note, 23 for water, 23 for ice. That is the final temperature of the mixture, so the whole system is at the same temperature. That is the equilibrium temperature. Okay, moving on from there, C for ice is 2100 joules per kilogram Kelvin, and the latent heat of ice is 336,000 joules per kilogram. Okay, and notice that in this there is no mention of temperature. So this event happens at constant temperature. Alright, moving right along here. So we have the law of heat exchange. And according to this, water is going to lose heat, and that will be mc delta T. Okay, that's simple enough. On this side, however, we have a little bit of a complication, and that's why this is a slightly harder problem. What is the complication? Okay, so starting out, we are saying that we have a piece of ice, and we are saying that that piece of ice not only melts but also gains enough energy for its temperature to rise to 23 degrees Celsius. So think about this. First of all, its temperature is negative 4.4. At that temperature, ice does not melt. Remember that melting point of ice is 0 degrees Celsius, which means that when its temperature is negative 4.4, first of all, it will acquire energy and its temperature will rise to 0 degrees Celsius. Once it's at 0 degrees Celsius, then it will melt. And when it starts melting, it will completely melt, remaining at 0 degrees Celsius. And then once all of the ice has become water at 0 degrees Celsius, then it will gain more energy from the water in the beaker, and its temperature will then rise from 0 to 23. So here we have three phases, three different things happening. We cannot, even though the mass is the same, we can't just say m times whatever and do it, because the value of C and L are different. And because of that, we have to do it as three parts. Now, of course, the mass is the same, so we can actually write it as a single factor. And you're good at doing that. You know math, so that shouldn't be a problem. But you have, oh come on, like that. You have mass, and let's put parentheses here. And now we have three parts. The first part is that the temperature rises from negative 4.4 to 0. So how much is the change in temperature? That would be 4.4 degrees Celsius or Kelvin. Okay, and we're not worried about units in this situation. Okay, times specific heat capacity of ice, because we're dealing with ice here. So, and that is 2100. Again, joules per kilogram Kelvin, but we're not concerned about the units in this phase. We know that our answer will come out kilogram because all the units are attached. So we know that the mass is going to be in kilograms. You can actually put kilograms here to help you remember, like I said before. Okay. Okay, and so now that is temperature times mass. Or, you know what, I'm going to put mass in here for now. Just so you can see what's going on. Okay, so we have that. Oh, for Pete's sake. Well, I'm not going to worry about that. Plus, once again, the same mass of ice. This time, now, after it has gained that amount of energy, after it has gained this amount of energy, its temperature will rise by 4.4 degrees. If it was at negative 4.4, it will rise by that much. and it will become 0. Now at 0 degrees Celsius, if you heat ice, it does not gain temperature. Instead, it melts. And when it melts, we have a different formula. We say M times L, right? And L in this case is 336,000. So that would be the energy required for the ice to melt. Okay, and then after that, we're not done yet. So we have this M mass of ice, which first gained temperature from negative 4.4 to 0. Then at 0 degrees Celsius, it completely melted. And now it's going to gain some more temperature and go to 23 degrees Celsius. So from going from 0 to 23, its temperature will rise by 23 degrees. What happened here? Oh. Alright, and then the mass we know is still M. You can put M on this side if you want. Now, at 0 degrees Celsius, all the ice melted and became water. So now when this temperature rises, it's not ice anymore. It is water that's warming up. And so we don't use 2100 anymore. We use instead the specific heat capacity of water, because it's water now. So you have to keep in mind of what is actually going on. You have to keep in touch with reality, so to speak. So even though it started off being ice, it's not ice anymore. It has become water, and so the specific heat capacity has a different value. Okay, and I think I can leave it right there. What do you say? No, let's put this value in here also. Okay, so now I don't have a lot of time. I'm going to put these values in. The mass of ice is 0.25 kilograms times C of water, is 4200 times the change in temperature of ice. It went from 25 to 23, and we always try to keep the temperature difference as positive, so that will just be 2. And this will be equal to this. Now remember that all we have now, the only variable is M. That's your equation right there. So if you solve that, you should get an answer. And the answer should work out to, I have done that for you also. Your final result should look kind of like this. And I'm going to change the font color so you can see clearly. So you have that on this side. You have M times 2100 times 4.4, this and this. And then when you solve it, M comes out to so many kilograms. Okay, and we are almost out of time, but I hope this makes sense. The point I'm trying to make here is that you have to do it in parts. Sometimes you can do it separately and add together, or do it in a single equation, however it works out. Okay, so looks like we did manage to complete this in one lecture. That is excellent, and I hope that this makes sense. If there are any questions about this or anything else, please remember to ask. Okay, thank you very much, and you have a nice evening.